Welcome to a lesson with Dr. Powell. Using our speedometer odometer idea of reading what the speedometer says for a given odometer reading, let's suppose that our position is represented by something like this, some function. We'll call it y is equal to t squared. This is our t-axis for time, and that's y. So we're just using t for x right now if we're thinking about speedometer odometer relationships, but really it doesn't matter. We could have used an x. All right, let's suppose then further that we would like to investigate what the speedometer would read right after 1 second, saying these are seconds and pretending these are meters. What would the speedometer read right there? Well, let's use their pretending principle. On an interval from 0 to 1, say, we can pretend that the interval is straight to approximate or see what the speedometer might read. That would mean that these 2 points would be the endpoints on a line, and we find the slope normally. Okay, well, let's see. In this function, this is a 1, so we can think rise over run. It'd be 1. So if we think about the interval 0, 1, we'd have rise over run a slope of just 1. All right. Well, let's pretend a little better. In the pretending principle, we're going to suppose the smaller the interval, the better the approximation that the curve is to a straight line. Let's try that. Let's try 1/2 going up. So let's do the interval from 1/2 to 1. Smaller interval, and it includes 1. And for ease, we're just going to let n be at the end point of the interval. Okay, so what's this slope? Well, if you plug 1/2 into this function, you're going to get a 4th right here. And let's erase this line here and look at what we have now. We're going to be looking at the slope of this line right here. Okay, so looks like 3/4 over a run of 1/2. So 3/4 over a run of 1/2, which would simply be just doubling this. So you'd end up getting 3/2 as your slope. Okay, so all right, well, that looks a little bit different, and it's probably more accurate since we're getting closer to the point 1 and we have a smaller interval. But let's do even better. Let's go a little bit closer. Maybe this time, let's go all the way to 0.9 and see what that is. Let's do 0.9. So at 0.9, this would be 0.81. So the rise from here to here would be 0.19. And the run is 0.1. So we're going to get 0.19 divided by 0.1, which is the same as 19 over 10. All right. Or if you like, just 1.9. So 1.9 is what we get when we take this interval, 0.9 to 1. Notice that these values right here should be getting closer to the actual slope right there at this line, at this point. Meaning we're going to look at this curve, and we're trying to see the line that this curve most looks like right at the t value of 1. The line that this curve most looks like as you narrow in and get closer and closer, as you get closer and closer and narrow in your view window, it's going to look more and more like a straight line. what is that straight line it's most looking like as your view window or your little intervals of time get smaller and smaller and smaller? Well, these things, guys, are actually getting closer and closer to 2. Now, 2 is the actual reading of the speedometer right at 1 second. We call that the instantaneous rate of change, the actual reading. In the next video, we'll show exactly why it's 2. And that's just an E, okay? Let's see, no, instantaneous, there we go. Instantaneous rate of change. And you see these other guys right here, this 1, 3 halves, and 1.9. These are not the instantaneous rate of change. They're approximations to the instantaneous rate of change, and they get better as we go. And they're over an interval where we had to do some pretending. Now, if we do it over an interval where we have to do some pretending, these are called not instantaneous rates of change, but average rates of change. See here how we take one point to another and we kind of say on average, this is the slope, what's happening. It's an average rate of change. Thanks for watching.